In 262144, Bessie is going to be downloading a game with a one-dimensional line. So this line is going to contain lots of different numbers, and if two numbers next to each other have the same value, then she can replace them with the next highest number. So we want to help Bessie find the largest number she can possibly merge to get. We can solve this question using dynamic programming. So if we look at the example test case, there are lots of different numbers we can make. So we can combine this, we can combine this, we could even combine these two to make 2. And so if we go through a couple examples, we'll realize that for every number we make, there are lots of different ranges we can use to make it. So when I say a range, I basically mean for this 2 to be made, the range is from 0 to 1, since these two combine to make 2. And then for this 3 here, the range is from 1 to 3, since all of the values from 1 to 3 combine to make that value. So our DP state is going to be DP I val, where I is going to be the index that our range starts. So if we were to look at this range here, the I value would be 1. And then we're going to have the second dimension as val, which is going to be the maximum value made. So for example, dp 1, 2 is going to be 2. So the value we store is going to be j, where j is the last element in our range. So we have from I to j, and in this case, in order to make 2, starting at 1, we're going to go 1, 2. So our last element here, the index is 2, so our value here is 2. Similarly, if I wanted to get the value of 3, dp1, 3 is going to be equal to 3, because we're going to start here, and then in order to make this 3 here, the end of the range is at index 3. And then one more. And then the final example, if I have something like dp0, 2, well, we know we're going to start at 0, and we want to make the value of 2. So when we go here, the element or the index we use is going to be 1. So that's basically the idea of the DP. So why is this DP useful? The question asks for the greatest possible value we can make. And when we create this DP, we're going to start off by initializing all of our values to -1. So if we have a range, which is dpij, or ival, and the value is not -1, that means there's a valid way, starting from this I index, to get this value. If it wasn't possible to get this value, then this would be -1. But if it's not -1, then we know it is possible to reach this value. So we're going to loop through all of the values possible. And then when we loop through, we're going to basically update the DP value and check if the value isn't -1. That means it is possible to make this value. So then our largest value, we'll just keep a variable that's going to keep track of the largest value possible, and that's just going to be the maximum of itself and whatever number, so that dp any number here, and then the value is equal to something that's not -1. So the basic way our DP is going to work is we're going to have dp index, or index starting value, and then the maximum value that we can make starting at this index, or actually the value we want to make starting at this index, and then it's going to be equal to the end index of the range. And the reason, by the way, we're going to make it the end index of the range is for our transition. And then at the very end, we're just going to, every time we loop through, we're going to check to see if the size or the value, so this value here, if this is able to create a value that's not -1, then our answer is just going to be the maximum of itself and this value. Okay, so in order to check what this value is, we're going to need a transition. And our transition is actually pretty simple. We're going to make the value right here. So let's take another example. If we have 1, 1, 1, 2, 1, 1, let's say we're starting at this index right here, and we want to make the value of 3. So what we can do is we can look at our previous DP value. So in this case, we can look at DP I value minus 1 plus 1. So DP I value minus 1 is going to be, in order to make 3, we need to basically first make 2 and then combine it with something else to make 3. Since once we have two 2's next to each other, we can make a 3. We're going to first check to see if we can make 2. And if we can make a 2, so if there is a valid value here, then we know that in order to make that 2, there's an ending index. So whatever index this is, we're going to go to the next index. So using this example test case, that would mean this index here, since these two are able to make the value of 2. So this is our end index, or this is the value of DPI val minus 1. And then since from I to that value, all of this is used to make val minus 1. So in order to make val, we're going to need to check the next value. So our index is going to be here. We're going to start from here. And then from here, we need to find out how to make another 2. Adjacent to this, and since this direction is blocked off, we have to go this way. So when we make another block here, we basically want to find whether or not we can make another block here that's also equal to val minus 1. And the easiest way to check this is we're going to go to DP, and then since we know that, again, this value right here is going to end here, or in this case, in the example, this value, then we're going to go to the next index, so this index, and then we're going to check to see if it's possible to make val minus 1. So in order to check to see if this chunk exists, we're going to use DP, that index, and then val minus 1. And if it is possible to make that if it is possible to make that value, then we can make this val minus 1. So if this one or this one exists, and this block or this one exists, then it is possible to make val starting from our current I. And so we'll just assign it that value. And then again, at the end, we just print out the maximum size. So we know the state, the transition, and the output. Let's go look at the code to see exactly how this is going to be implemented. We're going to start off by reading in the input. So we'll read an N, and then we're going to read in all of the values in the actual 1D game, and then we're going to create our DP. So for our DP, we're going to have SZ, or size. So even though the individual numbers in our game are going to be a maximum of 40, the actual maximum answer we have could be greater than that. So I've just set it to a big enough number, which in this case I've just put 60, and then we're going to create the maximum size, our answer, and our DP is going to have the size of N and the maximum size. So before we actually do the DP loops, we're going to have to initialize by setting all of the values of DPI and then the actual value in the input to I. And this just means if we're trying to make the number that this current index actually is, so in the inputs case, since it's 1, 1, 1, 2, then the value here, DP1, 1, is just going to be equal to 1. And that's just going to allow us to basically show that it is valid to make that value using this current DP. So for our DP loops, we're going to loop from val to I. So we're going to have two main loops. We're going to have val, or the maximum value, or the current value we're making, on the outside, and then we're going to have I, which is going to loop from n-1 to 0 on the inside. Our DP transition is going to be just like described earlier, DPI val, where val is the value we're trying to make, and I is the current index, and it's just going to be the maximum of itself, and this transition here, where it's the previous value plus 1. So that's just going to be the next index that we have. And then the value of val minus 1, so we can combine the two to make the current val. And in order to do this, since I've set this to -1, we're also going to have to take a look at some of the corner cases. So if anything here is equal to -1 or out of bounds or less than 0, we're just going to continue and not do the state. But if all of this is valid, then we're going to do our transition, and then we're going to check to see if our transition is valid. And since the answer just wants the maximum number we can get, I'm just going to keep this value max size, which is just going to be the size of itself and the value, provided that we can actually come up with a valid way to reach this value. So our output is just going to be maximum size, since that's what the question is asking for. And that's the end of our program.